Yes, we do, Miss Miller. Thanks, guys, for the response. Okay, so what's the balance equation? I know, I'm asking you what the balance equation is.
2, 2, 2, 2.
No, 2, 2, 2, 1. Good. Okay, so it's balanced now. Okay. And now we need to figure out how to approach the problem, right? So what is the given here, Hunter? Hunter? Okay, so 44.8 liters of H2, so hydrogen gas. All right. And then it says another condition. STP, right? Okay, we all see STP here. And then what's it asking us to solve for? Okay, and then separately, grams of water. And it's writing as HOH, so I wrote as HOH here as well. Okay, so Josh, how would you approach this problem? We did that, okay. Anushka, how would you start this problem?
You would start with the ideal gas law.
Potentially the ideal gas law. Where's all the pieces to the ideal gas law, though?
You need to find it's like the STP.
Okay, so this gives me two more givens, is what you're saying, okay? And then what would we be solving for using the ideal gas law? We would solve for moles of H2, right? Okay, now, that's working hard. There's actually an easier way to approach this. It was the STP thing that you guys always want to use. 22.4, right? Now we can use it. We can use it as a conversion factor. So if I want to use the 22.4, what is that? What is 22.4 again? 22.4 what? Per 1 mole of gas, right? So this is applying for any gas at STP. So I'm going to start with this, 44.8 liters of H2, and I'm going to immediately convert to what? Moles of itself, right? Using this. How do I use this? What goes on bottom? 22.4 goes on bottom. Cancels out those liters immediately, and then 1 mole of H2 goes on top. So we haven't had a chance to use this conversion factor in a while, so here it is again. STP conditions. Alright guys, so then now we can get to grams of sodium, right? I'm in moles of H2. Give me, what's the mole ratio here?
So 1 on the bottom.
1 for who?
1 mole of H2.
And you're getting that from the balanced chemical equation. Okay, so there's our 1. And then what goes on top? Okay, so what goes on top?
2 moles of
And you're pulling that from the coefficient as well. Good. All right, and then Garrett, last step. I'm solving for this first. Okay. Sodium on top. Good. So we did this just because it's at STP. Yay, we can use that conversion factor. We did the 2 to 1 from the mole ratio from the balanced chemical equation. And then the last piece we just did molar mass from the periodic table. Is this news to anybody? We kind of know how to do this. It's just thinking ideal gas law at the time kind of pigeonholes you into ideal gas law, but then we can remember that occasionally we're allowed to kind of circumvent the ideal gas law and use an easier route. Yeah.
How do you know you need to use the ideal gas?
Every other time, except for when you're converting liters to moles or moles to liters at STP. So when it gives you at STP, you're like, score, I don't have to use that ideal gas law, I can just go straight with using this. Okay? So STP, you can use that. Non-STP, ideal gas law. So the combined gas law, you have to have 2 pressures and 2 volumes and 2 temperatures. In this case, we only had liters and then this, so that's why we didn't use combined gas law, because there wasn't like a scenario 1, scenario 2. Okay? All right, so calculate, you guys can do this in your head. What's 44.8 divided by 22.4? 2. What's 2 times 2? 4. What's 4 times 23? 92-ish. Okay, so let's, how many sig-figs do I need here? 3, so 92.0 it is. Good job, guys. All right, so talk to your neighbor how this process would change for the solution of water, grams of water. How would we change the process when solving for water?
we just do now we just do something that has with water.
On maybe comes yeah, because I want to. All right, back to me. 3, 2, 1. Alex, how would this change if solving for grams of water?
We change the mole ratio to 1 mole of H2 and 2 moles of water.
Because there's 2 right there for water, so
Yeah.
we're just changing the identity, really. Okay.
And then on the next one, you just change 1 mole of Na to 1 mole of water, and then you change the grams to
Like 18, right? Water's 18-ish grams per mole. Right, so you guys know how to do that. Good. All right, pull out a piece of paper. We're gonna, or actually, we're gonna do 2 things. We're gonna finish that last piece of the foldable, the Dalton's law. Okay. And then we're gonna do our lab. Okay, so we will need a piece of paper for our lab in a second. Okay, so Dalton's law, and I think some of you guys already explored further, so you know how to get to Dalton's law. But everybody got the foldable out? Alright, I do want to see everybody's foldable because I have some people who are almost done and some people I haven't seen yet. Okay? So the foldable is due Monday. I'm taking PS14 and foldable Monday along with those 1 through 5 that were starting yesterday. I do want to kind of hit another 1 or 2 of those 1 through 5s with each today at the end of class. Okay, so everybody has their foldable out and I will see those shortly. Okay, so for the definition of Dalton's law, and you can kind of write your notes in your foldable at this point in time, it's the summation of partial pressures in a mixture of gases equals the total pressure. So when I say the word summation, what mathematical process comes to mind? Addition. This is like the simplest of them all, so save the best for last. So summation of partial pressures in a mixture of gases equals the total pressure. Thumbs up when you get there. Okay, so what we'll see is I will ask for a couple of different ways to think about this. I'm going to give you a real life scenario first, which is one of the pieces you're kind of supposed to have an example in your booklet, in your foldable. So a real life example can come from our atmospheric pressure and all the gases that are in our atmosphere. So shout out some of those gases for me.
Nitrogen.
How do I write nitrogen?
Oxygen.
N2, good. O2, CO2, carbon dioxide. What else?
How did you do that?
Okay, so what else, guys? Argon. Come on, guys. There's a couple more in our atmosphere.
Is it in the
Methane.
Second, probably if there's enough cow farts out there, there's methane.
helium.
Helium, very little, like, balloons have escapade. So what's that stuff that precipitates?
Water.
Water vapor, okay. So there's water vapor. I'll put like helium just because there's a little bit, there's a trace amount of that, there's a trace amount of hydrogen, there's a trace amount of lots of things. So there's more than this, but this is a good start. So all of these together, when we add them up, they should equal what our atmospheric pressure is. So at sea level, what's our atmospheric pressure? 1 atmosphere. So all these together should equal 1 atmosphere. But the way we show that, and in the equation or the formula for Dalton's law, we write P total, this is like the generic formula first, P total is equal to P1, P1 plus P2 plus P3 and so on. So it kind of depends on how many gases are in your mixture, which you're adding up, but the idea is that you can continue adding as much as you want. So for us, we'll say P of atmosphere is equal to P of nitrogen plus P of helium plus P of carbon dioxide plus P of oxygen plus P of argon plus P of water vapor, and the list goes on, but I think I captured everything you guys had here. So all of this collectively should equal what here? 1 atmosphere, right? So I could tell you each of these partial pressures except for 1, and you could solve for that 1. So I could say like partial pressure of nitrogen is like 0.71 atmospheres plus X, like you could solve for partial pressure of helium. I could tell you, gosh, I got it in my head, like 0.09 atmospheres for carbon dioxide plus like 0.2 for oxygen and like 0.005. Like I could keep making these up. This may not equal 1, but the idea is I could give you a lot of stuff, and all of these summate to 1. You could solve for x by doing what? Just subtract them all from 1. Okay. All right. So there's number 9. Maybe write this down for yourself later. Number 9 on PS 14. There's a water vapor pressure that's not given to you, that needs to be given to you for you to solve the problem, and it's 3.73 kPa at the 27 degrees Celsius temperature that it gave me in the problem. So number 9 on the problem set requires you to use Dalton's law. You need that piece to solve for number 9. Good? Did I put it in there? I don't think I did. Okay. I did put it in there? Okay. I'm a better person than I thought. Okay, because I was like, I'm pretty sure I forgot to do that. Okay, now lab. Pull up piece of paper, call it molar mass of butane. Yeah. Right over here. Interpret how to use variables. Oh, okay, yeah. Yeah. Guys, let's go. Come on. All right, guys. So here's the goal. Shh. Hush. The idea is not that you understand the formula of butane. You're going to collect data. You're going to collect data, and your data will be what you have to use to find the molar mass of butane. I know we're all smart cookies. We know the molar mass of butane at the back of our hand. I know you can find the molar mass by just adding it up, or you have to do it from experimental data. You cannot do it just by simply pulling data from your periodic table and moving on. If not, the lab would be done now, right? Because there's no reason to do it if you're not using experimental data. Okay, so one thing, I'm giving you a lighter. Okay, the lighter does not light. I've taken the flint out because our job is not to combust the gas. Our job is to collect the gas. We need to use the gas being butane. So when you put the lighter, you won't see any sparks. You'll smell the gas though. Do not do that in my room. Okay, so what we're going to do is we're going to put it underneath water. So you have these pneumatic troughs or troughs, and they're just a bucket of water. Okay, you're going to have water in here. And you're going to take your hand. Okay, there's your hand. And you're going to hold the lighter underwater, and you're going to light it. That's the lighter. Label this. Okay. And so the lighter's going to light, right? Well, what's going to come out of the lighter?
Yes.
Bubbles, right? Okay, so but we want to capture those bubbles. So we're going to use some glassware. We're going to capture those bubbles. That glassware is going to look like this. We're going to invert it. Okay, so we're going to invert it over the gas bubbles. What does that look like upside down? Graduated cylinder, right? So we're going to use a 100 ml grad sil, and from there we're going to collect the bubbles. There's going to be water in this grad sil first. So as the bubbles go up, what's going to happen to the water inside here? It's going to go down. It's water displacement, so it's pushing the water out. Eventually, the water level is going to equate to the water level in the bucket. At that point is when we stop. Okay? At that point, we're going to figure out the volume of our gas. So how are we going to figure out the volume of our gas? Look up the numbers on the grad sil, right? There might be 95, there might be 80, it might be 40. It kind of depends on how far down your grad sil is. Okay, so this whole time we're going to be collecting the temperature out of the experiment, and that experimental temperature is going to be influencing something called water vapor pressure. So I said this is happening in water, right? So not only are there gas bubbles that are made of butane coming up through here, what else is kind of following along with it? Water vapor, right? So there's little specks of water vapor just hanging out in here. So we can't really remove that water vapor, so we just have to embrace it and call it a day and move on to calculate with it. So what I've given you here is come and get your water vapor pressure. I have a link here and I'll pull it up on the board. At the temperature that your experiment's occurring, come and get your water vapor pressure for that. Maybe make a note to self. Board. P water vapor. Because that's where you're going to get it. It's not going to be from the experimental data. Another thing is, we live here in America. We don't believe in the metric system. We believe in the English units, right? So the Weather Channel says today the atmospheric pressure, aka barometric pressure, is 29 inches of mercury. That's what I said. Write this down because you're going to need that. Okay, so this is barometric pressure, but I have kindly given you how to convert from inches to centimeters. And that's really helping us get closer to a unit of pressure. What unit of pressure do you think I'm trying to get you to see here?
Millimeters.
Millimeters of mercury, right? So you guys have to convert from centimeters to millimeters of mercury. Okay, once you're done with that, I will tell you two more things. When you guys are ready, like butane will be up in the top of this grad still, right? You just drop those in the lab station for me, okay? So butane will be up here, right? I'm up here, people. I'm up here. So I don't want butane just to be released into my room because it's flammable. We're going to put it in the fume hood. We're going to cap it because it's going to be upside down. We're going to cap it with our hand, walk to the fume hood, turn it upside down in the fume hood, and release it into the wild. Okay? And that's going to be how we get rid of the gas. I don't want the gas just hanging out in my room. All right?
Yes.
All right. So the last thing here is, do you recognize this, what I'm trying to show you here? Whose law is this? Whose law is that? Dalton's law, okay? So Dalton's law, gas pressure, which is the butane, plus water vapor pressure equals what? Where would you find the total pressure? The atmosphere. Thank you. Okay. All right. So you have about 30 seconds to find a three-person lab group. Get to lab. Monomass butane. Three-person lab group. Three-person lab group. 5 minutes. Garrett, Will, and Will, I need you guys to get started. Get started in the lab. Let's go. All right, guys, we have 15 minutes. Let's knock this question out. We're going to try to start another one as well, okay? So, people in the back, quietly finish up and put your labs in the box. I'm videoing right now, but remember, I'm holding you responsible for 1 through 5. I'm helping you problem solve. We've done 1 and 3 already, right? Okay, let's get started on number 2. So everybody has their beginnings of like 1 through 5, like written down the givens. Yes. So everybody help me out here. Will, just leave at your lab station. Thank you. All right, what's one of the reactants, guys? Magnesium. Josh, you're not packing up. Finish up with me. What's the other reactant? Hydrochloric acid. So that's going to yield what? What kind of reaction is this? Okay, so magnesium is replacing who? Hydrogen. So hydrogen gets booted out to the coal to make what?
H2.
H2, and then who's the other product?
NaCl2.
Good. Magnesium chloride is in GCl2 because your 2 crosses down. So then how do I balance this? 2 in front of hydrochloric acid. Will and Garrett join me. We're doing number 2 on the 1 through 5, okay? This is like something I'm taking up from you guys on Monday, so let's try to knock out at least 2 more. All right, so notice we're given 2 pieces of information. We're given the 1.5 grams, 1.15 grams of magnesium, and then we're given this information. We're given it's 0.1 molar, and I have 150 milliliters of it, right? So I already know what kind of problem this is. What kind of problem is it? Knowing the stoic side of things. It's a limiting reagent, sorry, stoic side of things. It is a limiting reagent because I have one reactant and the other reactant. Neither one says excess, but they give you information for both. So what do you have to do? Figure out what I have and what I need. Okay, so have is what unit here? What do I have to find units wise? Moles, right? Because these are mole ratios. I have to find everything moles. So take this to moles. 1.15 grams, 24.31 grams per mole. How many moles is that? Louder for me. 0.047 moles, okay? And then how do I get to moles from molarity?
Number of moles over 1 liter.
That is the number of moles over 1 liter, right? So molarity is 0.1 moles per liter. Times it by the
volume.
The volume in milliliters? In liters, right? So basically doing liters times moles per liter. What cancels? Liters, so we get moles. Okay, so what is 0.1? I'm just going to back that decimal up. I'm not going to really convert. Okay, so that's 0.150 liters. Okay, so what's 0.150 times 0.1? Okay, so that's 0.0150 moles. Okay, so some of you guys asked me about a BDA before, during, and after chart. It's something that I teach with AP. It's more advanced. I used to teach in honors, but most people were like, don't get it. Something that's a little bit nonsense. So I'm going to show it to you really as the cheapest way I can right now, okay? So I already know that the ratio is 1 to 2. I can see that I have this much before the reaction. I have this much of the Mg and I have this much of the HCl. Think about it. Think about the ratios. Who's going to run out first? Just think about it. Yeah, hydrochloric acid, right? Because I should have a 1 to 2 ratio, right? So magnesium, I have this much of it. I should have double that of the HCl. So do I have double that? No, so what's going to happen? HCl is going to run out, right? So this is my LR. Now the only reason I need the LR is because I need to find something that I'm going to plug into the ideal gas law. So notice in the beginning I have T, I have P, and I have question B, right? The last B is a separate kind of question. So I'm looking for B. B of what? The gas. Who's the gas? Okay, so who's it? Hydrogen gas. Okay, so this is my gas. So I have to find, I have the P, I have the T, and I'm looking for V of the gas. So what else do I need to plug into the ideal gas law? Moles of the... No, guys, it's got to be the ideal gas law, right? So it's got to be the gas. So I don't have moles of the gas yet, right? That's my problem. So now that I know that this is my limiting reagent, I've got moles of HCl. How do I get to moles of gas?
Using that one.
Using this limiting reagent and soy. Right. So give me some moles of gas. 1 mole of H2 over. And where are you getting this 2 from? The mole ratio. Good. So we needed to know who the LR was so we could proceed to find the moles of hydrogen gas so we can then proceed to the what? Okay, so this is going to be moles of H, so this is N. Okay, so now I'm able to proceed on to what? The ideal gas law. Given this temperature and this pressure and looking for volume. Okay? All right, so let's solve for volume. I'm going to kind of do this quickly here. So we have P, V equals nRT. Solving for V, right? So divide by, I'm dividing by P. Okay, so V is equal to nRT over P. What's N?
0.007.
Okay. 0.0075 moles of hydrogen gas. What's R? Atmospheres, liters per moles. Okay. Okay. What's T?
298.
Right, it said 25 degrees Celsius, but it means wants you to go to Kelvin, so it's 298 Kelvin. And we're going to divide that by what? Okay, so it was what? It was like 7. Yeah. So you can. How did you convert that to atmospheres?
Divided by 760.
And that was how many atmospheres? 9763. Okay, so what cancels? ATMs cancel. Moles cancel. K cancels, right? So then liters are left. What's my volume here?
0.9.
No. 0.19. I think it was like 188.
Yeah, but
so yeah, I'm gonna not go to sig figs just yet, just for a hot second. So this, when you divide, you get 0.188 liters. This is of hydrogen gas. So let's go look at the question again. All right, people in the back, you guys should be really close to done. Okay, wrap this up in the box. All the way back up here, what's the second question? So when I find percent yield, what am I doing? So actual over theoretical times 100, right? Which of these volumes, the one stated in the problem or the one we calculated, which is actual? Stated in the problem because it says they captured, like they collected this in the lab. So this is actual yield. So what did we do? Yeah, we were like, La La Land, if we had a perfect reaction, this was the LR and everything was cool and there was no humans involved because humans create error, then we're going to get perfectly this amount of volume, but notice this is in liters, that was in milliliters, what do I need to do? I want to convert this one to, right, so that's 188 milliliters because there's 1,000 milliliters, so we divide by, or multiply by 1,000. So now we can do actual yield over theoretical yield times 100. Actual is what? Was it 149 milliliters?
Yeah.
Divided by 188. And then times 100 is what? 79.3% yield. Not too shabby. I'd let them stay in the lab group. Not too bad. All right, so that was that's 3 done now, right?
Yeah.
Okay, so take a breather. Look at 4. And ask me questions. Yeah. Moles in number 4. Okay, so there was one word that kind of maybe threw you off, and yeah. So the word oxidation state just means that it has a 2+ charge. So I want you first to tell me, how did you guys write this reaction? Because you were supposed to kind of look ahead and get started. How did you write this reaction? All right, maybe you should write the reaction real fast. X plus what? Okay, so I'm going to put M for metal. Okay, so M plus what sulfuric acid? Okay, H2SO4. What does that produce? What kind of reaction is this? Single placement, so who gets booted? Hydrogen gas. And metal gets with who? SO4. Sulfate, right? So if metal, I told you it has an oxidation state of 2. Metal has a 2+ charge. What's the charge of sulfate? 2 minus, right? So what's this written out? MSO4, right? Because the 2's cancel each other out. Okay, so balance that. Oh, it looks like it's balanced. Okay, we're good to go, right? Yeah, we're good to go. Okay. So M is just an imaginary or made up metal. We are going to talk about the metal identity at the end. Okay, guys. So look at all the givens here. What do you have to find? We have to find moles. Okay, so that would be moles of what in our moles of what? Well, what did you just plug in? Like, so you saw temperature and pressure and milliliters of gas. So what do you think you found the moles of? The gas, right? We're using the ideal gas law. You're not finding moles. There's no ideal mole or ideal metal law. It's ideal gas law. So when you use all this information, you're going to solve for moles of gas, which is moles of who? Which is moles of who? H2. And then you're going to show me how you get back to metal, which is what? Mole ratio. I know it's a 1-to-1. You're like, it doesn't change the number, but you still need to show that process. Once you get to moles of metal, and then you see this information up here, how do you get to molar mass? Just take grams and divide by moles. Okay, just like you did in your lab. Grams given, divided by the moles that you took and you converted over to moles of metal. That's it. Okay? All right, so my people who are like with me because you kind of got started putting these together, okay? You good? Okay, number 5, how are we on 5? You did? I thought that one was easier than the others. Okay. So 5, you're asking for V, right? I'm kind of laying down the foundation. You guys are calculating, okay? You got your volume, you got your temperature, you got your atmospheres. And then what are you going to have to do with this? Convert this to moles of sodium, right? And then, but sodium is a metal, right? So we can't plug that in the ideal gas law. You'll convert that further to what? Moles of chlorine, right? So you have to have a mole ratio. So let's go ahead and find that rate or the reaction. Notice it says sodium metal to form sodium chloride from chlorine gas. All right, so what's one of the products? The product. Sodium chloride, NaCl, okay? From what two reactants? So Na and higher rate chlorine, Cl2, so then I need a 1, 2, 2, yeah, okay. All right, so guys, once you get your grams of sodium to moles of sodium to moles of chlorine, you have N, you have T, you have P, you look for V. You got it? Okay. And then you guys can find the last one, BS4.
Good afternoon. Bus announcement for the day, bus is 325, it's bus 542, bus 141 will be 15 minutes late, 2 on the wait to come. Bus 308 will be 15 minutes late, students on the wait to come as well. Thank you and have a good holiday.
Three, two, one. Okay, you're perfect in all ways. Thank you for being here today. Thank you for cleaning your lab. Lab's in the box, right? Yeah. Okay. Be sure to check over like the break, kind of if you have any missing work to get that into. Who's almost done with their photo? Okay, basically everybody, you should be, because we talked about that a while ago. I'm taking the foldable Monday. I'm taking the test for Have a great break.
We don't even run the same bus anymore. We ride 396.
We've been on that bus.
You ride 396?
But we've been on that bus.
No, we used to ride 369. Now I ride 396.
Oh,
No, I don't know.
Really? Bye, guys.
that was. I don't know. We must have. I feel like I wanted to. I told him to. We didn't shake it out like the first.
They get the water out of it.
The first time around when we masked it, I don't think we shook all the water out of it.
That's what that's usually what side note, are you considering taking it?
Maybe senior year probably.
Well, you're obviously very good at what you're doing here. Like, and I would advise you to use your space, but what would you do?
I don't know. Anything science.
Okay, so you're probably gonna take this in college. Take if you take teacher at all in college in your high school career. Take it next year because you'll probably have more credits.
Okay.
So it makes more sense if you have to do out at all.
Yeah.
Chemistry helps not only knowledge,
Definitely.
consider that, okay? Bye again. And get Matt to sign up too. Yeah. Listen, bye.
No! Get out of there.
And then I saw that my reminder and I was like,
Well, there you go. That's what I have to do all the time. Yeah.
I was like,
You're good. Bye, Hallie.